we're going to pick up exactly where we left off in the last class, just a couple of steps back. So where we left off, let me see how many people are in the class. They're still kind of trickling in. And since we will be covering a lot in this class, if you missed this class, you're probably missing a lot. Anyway, so here's where we are. Can you see my mouse, folks? Raise your hand if you can see my mouse.
Yes.
Okay.
Wait, no, I can't. There it is. There
Okay. So the way we defined it, we said that to train the network, it's the CNN. It's just like training a standard MLP. You're given positive and negative training instances with labels. We will use gradient descent, and during for training, we need to compute derivatives for all of the parameters. And so to do this, we will pass each training instance through the network, compute the divergence between the output of the network and the desired output, and propagate the derivatives backwards. Now, the final MLP is standard, so you can just propagate the derivatives using standard backprop rules all the way to the end of this final MLP. Now, this final layer here, the first layer of the MLP is basically just a unrolling of the last convolutional layer. So these derivatives can be folded back into the same shape as the last layer of the convolution. And then subsequently, we have to pass those derivatives backwards, and this is where we needed adjustments. So the point was, going forward, you had computed at each time, you had computed the output activation maps for each layer. Again, remember, each filter, this confusion has arisen again and again over Piazza. All of these are equivalent. You're scanning the input with a distributed representation, MLP. So every neuron in the network, every base neuron in the network represents one pattern that you're trying to detect. So the neurons in the MLP we're also calling them filters. And for some unknown reason, we are also calling them channels. So every single neuron in each layer is going to produce one of these maps. And to compute the map, you first computed an activation map, which computed just the affine functions of the input. And then you applied an activation function to it pointwise. And so this is going to be the activation sequence of activation maps coming out of the previous layer. And then we convolved this collection of activation maps, which we could stack into a cuboid with several filters. Each filter had many planes. You had one plane for each one of these maps. And so each filter will produce one of these affine maps at the output. So each filter operates on the activation maps of the L-1th layer to produce one affine map of the Lth layer. And the way it works, every plane of the filter convolves the corresponding activation map of the previous layer. So each of these planes is going to convolve one of these guys. Eventually, these convolutions are going to give you as many results as you have activation maps in the previous layer. You sum them all up. And when you sum them up, you're going to get one of these affine maps over here. So if you have D filters, each of these D filters is going to produce one affine map in the next layer, and then we will apply activations pointwise to them to get the activation maps of the next layer. So this is for the convolution layer. Again, each of these represents a channel. Each channel is computed using one filter, which is also called one neuron, right? So does everybody get that bit of terminology, guys? Questions? Raise your hand if you have any issues. Raise your hands if you got it. I'll wait. I want to see at least 50 hands raised. Okay, thank you. So here's what happens. When we compute our derivatives, going backwards, we are going to compute our derivatives till this point. And then when we go back, There are two kinds of layers we saw. We saw convolution layers and we have pooling layers. And we have to make adjustments to how the derivatives are computed for each of these two types of layers. So for the convolution layer, you're going to assume that you've got the derivatives all the way to the activation maps, which means that you have computed the derivative of the divergence with respect to every element of every activation map in the Lth layer. And now the question is, how do you propagate those back to compute the derivatives for the affine map, which is Z of L, and then how do you propagate them further back to compute the derivatives for the activation maps of the previous layer, which is YL minus 1. And in the process, how do you also compute the derivatives for each of the filters that we are using, that we are operating on operating over these guys with to compute these affine maps. And similarly, for the pooling and downsampling layers, you're going to assume that you have the derivatives with respect to these y's, which is the output maps of the pooling, and then we have to figure out how to compute the derivatives going backwards to the input of the pooling. Now, this is what we're going to take a look at. So we have two sets of things to compute. For the convolution layers, given the derivatives with respect to the activation maps, first we have to figure out how to compute the derivatives with respect to the affine maps. Given the derivative with respect to the affine maps, we have to compute we have to figure out how to compute the derivative with respect to the activation maps of the previous layer and the filters that operated on those activation maps to compute the affine maps. For the pooling layers, given the derivatives with respect to the output of the pooling, we have to figure out how to compute the derivatives with respect to the input. So we saw this bit as, again, this is a recap from last class. Let's focus on the convolution layers first. And for the first part of it, let's look at how to compute the derivatives for Z given the derivative for Y. And this was easy, right? Each activation map, on each activation map, you apply on each affine map, you apply an activation function pointwise to get the corresponding activation map. So you apply a pointwise activation function on each element of every plane in Z to get the corresponding element in Y. So going backwards, if you already have the derivative for Y, then again, this is pointwise. All you have to do is to multiply the derivative for Y with the derivative of the activation function at the corresponding value of Z, which was computed going forward. And in that process, you can now compute the derivatives for all of these affine maps. So again, I'm distinguishing between the affine map and the activation map. The affine map is what you get after the convolution with the weights, the filters. And the activation map is what you get when you apply the activation function to the affine map. So we figured this first step out. And where we had stopped in the last class was how do you actually have the derivatives with respect to the affine maps in the Lth layer. How can I propagate those derivatives backwards to compute the derivatives for the activation maps for the previous layer and the filters, the weights that operated on these guys to compute these terms. And so again, in the forward computation, we compute these affine maps from the previous layer activation maps and the filters. So during backpropagation, given the derivatives with respect to every element of every affine map in the Lth layer, we must figure out how to compute the derivative for every element of every activation map in the L-1th layer. We must also figure out how to compute the derivative for every element of every filter, which is, again, the filter is just your scanning neuron, right, for the Lth layer. So let's take a look at this guy first. Now, we've computed the derivative here. We want to take this backwards all the way to the previous layer activation map. Now, if you consider the nth affine map of the Lth layer, the nth affine map is obtained by convolving the activation maps of the L-1th layer by the nth filter. Again, the nth filter has as many of these little planes. Again, the filter is a cuboid, but I can think of this as having many planes, one per affine map in the L-1th layer. Again, this is just referring to notation we've been using through the past classes. So every one of these maps convolves with the corresponding filter and contributes to this guy. So the mth affine map convolves with WMN. The second index represents the destination. And so the first index represents the source. So every activation map, the mth activation map convolves with WMN to contribute to the nth affine map. And so every activation map influences every affine map, and every one of these affine maps in turn influence the divergence. This is just a linear picture. So going backwards, this means that every activation map influences every, in the L-1th layer, influences every affine map in the Lth layer, all of which in turn influence the divergence. So now, if I want to compute the derivatives for this one guy, I want to compute the derivatives of the divergence with respect to every element of the mth activation map in the L-1th layer. I have to see how these terms connect to the divergence, and this is how they do it. This activation map influences every affine map, and all of these influence the divergence. And so, if I want to compute the derivative of the divergence with respect to the elements of this map, I have to sum over all of these affine maps, and the term I sum is the product of the derivative of the divergence with respect to the affine map times the derivative of the affine map with respect to the elements of the affine map, every single element of the affine map with respect to every single element of Y. And so this first term, we are assuming we already have. The second term is what we really have to compute. This is where we stopped in the last class. Does everybody remember? Raise your hands if you remember. Yes. I'll just wait till we have 50 hands raised. There are only 100 people in class, so I'm going to be considering today's class as another of my attendance classes, which means we will check if everyone in classes watched the video. All right. So there is a poll. TS, can you show the poll for slide 163? Yeah. We'll stop this in 5 seconds. Okay. So both of them are true, right? This is where we stopped. Now, to see how this is, right? To see how we can compute this, the derivatives for every element of this map. Let's take a look at how each element, now this is element wise for every element of the map. Let's take a look at how that element influences things in the activation maps in the next layer. And we're trying to sort of focus on this term. And specifically, let's just take a look at one of these links because it's symmetric. I can apply the same rules for all of these maps. How do the elements of this mth map influence the elements of the mth activation map in the L-1th layer, influence the elements of the nth affine map of the Lth layer? Let's take a look at this carefully. So Consider this one single element. We've seen this video before, right? Let's consider this one single element of the Y map, say the one outlined in red. Now, this is the entire mth activation map. This is the nth affine map of the next layer that I'm trying to compute. To compute the affine map in the top left corner, I place the filter on the top left corner of the activation map, and then I perform an inner product, a component-wise product, and a summation. We've seen this. Now, if an element, if I want to see if an element over here has influenced a specific element here, this element has influenced the corresponding Z entry if it falls within the filter region, because that means this is actually contributing to the Z. So let's look at all of the elements of Z that this particular element in Y contributes to. Let's just take a look at the animation. You can see how many different elements in the next Z layer it influences. So it turns out that this one guy has been used in the computation of all four of these elements of the affine map in the next layer. In fact, here we are only looking at one of these planes, but then in fact this guy, this one element of the of this mth activation map would have contributed to these four elements of every single affine map in the next layer. Now, again, let me focus. Remember, we're focusing on just one of these guys to compute our derivatives. So let's just consider one element, one of these affine maps, keeping in mind that this element actually, any element in this map contributes to all the affine maps in the next layer, right? So this is the mth activation map of the L-1th layer. This is the nth affine map of the Lth layer. This is the mth plane of the nth filter. So the filter I'm assuming is 3 cross 3, and I have marked the locations of each of the filter elements, the indices, but I'm using a double coding for the filter. I'm not only marking the location, every one of these elements has a different color. We will use this color as an indicator in future slides. So now consider, we're going to look at how this 2-2 element of the Y map influences the elements of Z. Now consider the 0-0 position of Z, right? The 0-0 position of Z. To compute the 0-0 position of Z, we place the filter starting at the 0-0 location of Y, and then did a component-wise addition, multiplication, multiplication and a summation. So the 2-2 element of the map multiplied the 2-2 element of the filter, as you can see. And that term, so Y22 multiplied W22 to contribute to Z00. Now, if I'm considering Z10, this entire filter has slid one forward. And so now on the 2-2 element of Y, you are now placing the 1-2 element of the filter, as you can see from the color. And so Y22 multiplies W112 to give you the 10 element of Z. And so also, if I want to compute the 20 element of Z, Y22 multiplies Z, the W02. So the Y22 multiplies W02 to compute Z20. And so I can continue this computation. And what I have shown you over here is something interesting. The index over here is the index of the Z element itself, but the color over here shows you which component of Y multiplied Y of the filter multiplied Y22 to compute this element of Z. Now, so Z22 over here, for example, if I'm computing Z22, it's this element of Z that is obtained in part by multiplying Y22 by W00. And observe something over here. because of the way we did the computation, the index of the z element and the indices of the filter element sum up to the indices of y. And that's obvious. That's because we are placing the filter starting at the location where you want to compute the z, right? And so if I want to compute the z element here, I'm placing the filter starting at this location. And so the index of the filter is the gap, how many steps you have to take from here to the 2 element, right? Which means that the index of the filter and the index of z must sum up to the index of the corresponding y. Did that make sense to everyone? Questions? Questions here, guys? Anything on chat? Is anybody paying attention? Right. So TAs, anything on chat?
No, nothing on
No.
that.
Nothing yet. All right. So generalizing that, for any x prime y prime element of z, I will be, if I want to find the contribution of any xy element of y to any x prime y prime element of z, then zx prime y prime is going to get a contribution yxy times w of x minus x prime y minus y prime. The indices of the weights and the location in z sum up to the indices of the y element. This is something we're going to sort of tee off of. And so when I compute, if I want to compute the derivative for yxy, the additive contribution to this derivative is obviously going to be the derivative of for zx prime y prime times the weight x minus x prime y minus y prime. Again, these two indices are going to sum up to the index for y, the element for which I'm computing the derivative, right? And so again, it's not just, so this is the contribution of a single position, x prime, y prime of the z plane. If I want to compute, get the contribution of a single x prime, y prime to the derivative of xy, that's just going to pick one of these guys. And the contribution of that one element is going to be the derivative there itself times the weight at the position at the index by which you have, at the index which you have to add to this location to get here. So given this, to actually compute the derivative for yx, overloading these variables at xy, I have to sum over the entire z map. So I'll be summing over all possible values of x prime, y prime. And that's just the contribution of one map, right? So because we know that this guy contributes to, influences all of the affine maps at the next layer, after having computed this term for each of these individual maps, I'm also going to be summing over all of the affine maps. And so this here is the function that you can simply implement to compute the derivative for yxy, given the derivatives for every element of every affine map in the next layer. Now, this equation looks kind of slightly complex. What is it exactly? It turns out this is just a convolution. So let's see how. Let me go back to this picture, right? So I know that to contribute, if I want to look at, if I want to see the contribution of any x prime xy element of y to z x prime y prime, then I'm just going to be multiplying yxy by the weights at x minus x prime, y minus y prime. So ignore the equation for now, okay? Look at the pictures and the colors. This element over here, so to compute the derivative for this element, let me see if I have the rest of the pictures. Oh my, just give me a second. My slides have not updated, how annoying. This is the problem with working on multiple computers. They don't sync. Okay. Now, consider this 2, 2 element, right? So Z00 was obtained in part by multiplying Y22 by W22. So the derivative for Y22 has its additive contribution, the derivative at Z00 times W22. So the derivative at this location times the weight index, the weight whose index is shown by the color. This is where the colors come in. That's the 2, 2 index, right? But then if I move the filter forward, this guy contributed to Z10. So the derivative for Y22 now also has a contribution of the derivative at Z10 times the weight with which it was multiplied, the weight with which Y22 was multiplied, which is this weight 12. I'm showing this using the color again, right? And then if this filter slid forward, Y22 influenced Z22 through this W02, as we have in this formula here. So to compute the derivative at Y22, you have to multiply the derivative at Z20 by the weight at 02. So again, the color shows which weight it's being multiplied by. And so I can go through this entire sequence, and this little equation, this little picture shows you the full pattern for what are the sets of weights that multiply the corresponding elements of the derivatives for z in contributing to the derivative at y22. So here's what happened. We look at the color pattern over here. This color pattern is exactly the same as the color pattern for the filter, except it's flipped left, right, and flipped top, bottom, right? And so what we did was we flipped this weight vector, this filter, left, right, and top, bottom. We placed it with the bottom right corner at 2, 2 on the derivative map for the z, and then computed an inner product, and that gave you the contribution of this one map to y22. Or more generally, if I were to be looking at any xy position, then you'd get exactly, if you work through the arithmetic, you'd get exactly the same thing. You'd be flipping the filter left, right, top, bottom, placing the filter with the bottom right corner at xy on the z map, and then computing an inner product, and that will give you the derivative at xy for the y map. So if this is the mth plane of the nth filter, you're going to flip it. You're going to position it with the bottom right corner of the flipped filter on the derivatives for the nth affine map in the nth layer, computing an inner product, and that's going to give you the derivatives at xy for the mth activation map for the n-1th layer, L-1th layer. Did you guys get this visualization? Guys?
Yes.
Yes, right? So again, this is the equation, right? That's literally what this equation says, that you're flipping the filter and putting this with the bottom right corner at the location where you want to compute the derivative. But then, so here is the so this is true for any xy, right? So this is exactly what how the derivative is going to be computed. So let's say this is the map of derivatives for the nth layer, for the nth affine map of the nth layer, right? The nth channel. Just the affine, again, affine map is the channel, right? Our channel output. So this is the derivative for the nth channel of the nth layer. and this is the derivatives for the affine values of the nth channel of the nth layer. You want to compute its contribution to the derivatives for the mth activation map for the L-1 layer. So, and you have this corresponding filter which connects these two. The first thing you will do is you will flip the filter left, right, top, bottom. Then remember, you also want to compute the derivative for this top left corner, right? So if you, for that means you want to place this flipped filter with this bottom right corner at the top left box here. In order to accommodate that, you've got to pad this guy with k-1 zeros and columns and rows of zeros and on every side. And then you place this flipped filter. This is a flipped filter with the bottom right corner first at this location. Compute the inner product and you get the derivative, the contribution of this one map to the derivative here. Then you keep sliding it forward and keep performing the computation exactly the same way. And what is this operation, guys? Anybody want to tell me what this operation is?
It looks like a full convolution.
It's just a regular convolution of one map, right? After it's been zero padded. All you did was you took the derivative map for the affine function, you flipped the filter, you zero padded it, and then you convolved it with the flipped map. And so this gives you the contribution of this one map to the previous layer activation map. But then again, remember that you have to consider all of the affine maps in the nth layer, in the lth layer. It's not sufficient to consider just one. So what you will do is this, and this is where it gets really interesting. To compute the derivative contribution of say the first affine map to the mth activation map, you considered the mth plane of the first filter. To consider the contribution of the second map, you consider the mth plane of the second filter, and so on. So to consider the contributions of all of these maps, for each affine map, you have to compute the contribution of each of these affine maps to the mth activation map of the previous layer. You have to pick up the mth plane of the filter that was used to compute the affine map. These guys. Did this make sense? Raise your hands.
We have a question, Professor.
Yeah, yes.
It says, is the flip of the filter due to the parallel to the traditional convolution operation?
So pardon me?
So the question is the flip of the filter due
exactly. No. So this is the flip of the filter is due to the deconvolution operation. Literally what we're doing is you're going backwards. Remember, whether you flip it or not, think of these guys as being the flipped filter in your traditional convolution operation. That's all. So because the initial flipping and that you use in your signal processing convolution operation, that's sort of built into these filters going backwards. So when you're trying to compute the derivatives going back, you go back to the original filter. But anyway, that's kind of slightly tangential to what we are trying to say here. You see why I'm picking this row of filters, this row of planes from all of the filters to compute this guy, right? And so here is how the actual derivative for this mth activation map is computed. These are all the derivative maps for the nth layer affine maps, okay? Affine terms. Now these guys, these are all, this is not one filter, this is the collection of mth planes of each of my filters. So this thing to the, this layer, this set of planes from all of these filters, that's what I've written down over here. I'm going to have one of these for every one of these guys, right? Because I have as many filters as I have affine maps. The first thing I will do is flip each of these guys left, right, top, bottom. I will zero pad each of these guys. And then I'll place these flip filters over here, compute the inner product and sum over the entire lot. And so this is the actual computation that happens when you compute the derivative for the mth activation map of the L-1 layer. Oh geez. My laptop just decided it has to begin going to spinning mode. So questions, guys? Any questions while my laptop spins itself to exhaustion?
Yeah, Professor, can I ask a question about, will we cover about the bias later?
So this is terrible. I've not actually explicitly considered the bias, but if you think of the bias is just an additive term. So each of these guys is going to have just one bias term. You're right. Remind me to add this to my slides. But the bias is actually just a very simplified word, very simple extra term in the whole process. I haven't actually put it in the slides. It's my mistake. Wasn't thinking of it. But for now, assume there's no bias. I'll take this offline onto Piazza. Oh gosh, this is just going to spin. Any other questions, boys, while I wait for my laptop to do its thing? I have no idea why this is happening. Why?
So this seems like really huge and lots of computations that need to take place. Is this can we only do this because of the modern computing?
Well, you're already doing this in your CNNs, aren't you?
Yeah.
So this is no different from your forward operation, right? And so here is the actual computation that happens. This is how you actually compute the derivatives for each of the activation maps in the L-1 layer. This figure actually sort of illustrate the computation process over here. You pick the mth planes, you flip them, and then you convolve the collection of these guys, right? Now, one thing you observe is I'm continuing the convolution beyond the bottom right position. After this, so long as these filters have even one element overlapping with these maps, I'm continuing the convolution. Why is that? Anybody want to tell me? Why am I continuing the convolution all the way to the end?
Because your activation map is larger than your affine map?
The activation map, remember, when we were going forward, we lost the bound. If I was convolving some m cross m activation map by a k cross k filter, in the forward process we lost k-1 rows and k-1 columns, right? So going backwards, you recover them. This guy, obviously, look at it this way, this element influences, because the filter, because the filter would actually be positioned here, this element influences this position in the Z-map, right? And therefore, this position in the Z-map can be used to compute the derivative out here, which is this location of the padded structure. So you're basically recovering the k-1 layers and columns that you lost when you go back. Does that make sense? You lost them going forward, you're getting them back going back. Questions? There's an obvious question here. I'm waiting for someone to ask it. Anyone? So what would happen if I zero padded going forward? Remember, we were zero padding going forward because we didn't want to lose those k-1 rows and columns, right? Anyone remember that?
Yes, Professor.
Okay, so what? Raise your hands if you remember that. Oh, wait. I want to see 50 hands raised. Okay, and so when you compute the derivatives going back, you should be able to compute the derivatives for the elements that you actually, for the indices that you actually lost as well, right? the zero padding in this process of, yes, Ron, what's the question?
No, no.
Okay, so when you go back, you recover those locations. So what happens if you zero pad? Remember, if you only had a 3x3 and you wanted to retain the 3x3, you zero padded things going forward, remember? So what will happen is if you use this process, you're going to compute the derivatives for the zero padded thing that you actually convolved. And so you will have to throw out the zero pad, the derivatives computed for these zero pad regions, because they are not going backwards, right? They're not. So, and that's all you do.
Professor, we need a poll for 252. Should we do that?
Yeah.
Okay, let's do the poll.
There's a poll, guys. Can you show it up? Yeah. Okay, 10 seconds, guys. That's obviously true. This is what we've been saying all this time, right? Okay. Now, there's another thing. What happens if you are downsampling going forward? So if you're down, this whole operation only accounts for a convolution with a stride of 1, right? What would happen if you had a convolution with a stride greater than 1? Anyone? Does anybody want to hazard a guess? Why is everybody so quiet? I'll wait till somebody hazards a guess. Yes, Ramneet?
Wouldn't it be essentially the same, but you'd be striding as well again?
So not entirely, right?
Okay.
So I'll skip these slides because they're not important. But here's what happens when I convolve a map with a stride, let's say of 2. This kind of convolution of this map with this filter would have given me over here, if I use a stride of 2, I'm only going to get a 2x2 output, right? But this is strictly the same as convolving with a stride of 1 and then dropping every second element. Does it make sense?
Yes.
Right? Or convolving with a stride of b is the same as convolving with a stride of 1 and dropping b minus 1 elements of b minus 1, every b minus 1th element as you go forward, right? In every direction. So when you're computing the derivatives coming backward, this is the set of derivatives for the downsampled map that you actually computed. What we will need to do is to go back from it and compute the derivatives for the complete map from which we dropped a bunch of elements. So I can compose this derivative over here and fill up these derivative values at the specific locations which were copied down. What about the rest of these guys? What will those values be?
0.
Yeah, why?
Because they don't exist. They didn't contribute to anything.
They didn't contribute to anything. So now I can fill these guys up with zeros, right? And now that I have the complete derivative map with a stride of 1, I can go back and compute the derivatives for these guys. Did that make sense? Raise your hands if that made sense, guys. Okay, 50 hands. I will stop there. So here is the overall algorithm for computing the derivatives with respect to the previous layer's activation map. First, you have the derivatives with respect to the affine maps of the next layer. then if the stride going forward was greater than 1, you're going to upsample everything by introducing zeros. And then you're just going to, for every activation map, you're going to take the corresponding rows of all the filters, flip them, and then convolve the zero padded upsampled derivative maps for the activation, for the affine maps, and you will compute your derivatives. So I have this in pseudocode over here. I'll skip the pseudocode. The pseudocode includes the zero padding and the upsampling, and I even have the pseudocode for the upsampling. So here's where we stand. We have figured out how to compute the derivatives with respect to the activation maps for the previous layer, given the derivatives with respect to the elements of the affine maps of the current layer. The next thing we want is how do we compute the derivatives with respect to the weights. And so let's take a look. Now again, this is my miserable attempt at animation using MATLAB, and MATLAB likes to keep changing colors. But the point I wanted to make was that this filter, which is shown in green, influences every single position in the Z map, right? So it goes without saying that every single position in the Z map is going to contribute to the derivative of this filter. So let's take a look at how the filter affects the Z maps. Here's the whole example again. Consider convolving one particular layer of activation maps with one specific filter. So the set of squares over here shows the filter, and this is the equation for going for the forward computation. Within each map, you go over the region of the filter, perform a component-wise multiply and an add, and then you add a bias. I should deal with the bias for the backward as well. And then you sum over all of these to get you this one element, right? Now, consider the contribution of just this one element. You're ignoring all the other elements of the filter, just this one element. So this is the 1, 2 element of the nth of the, let's call it the mth plane, although this is really the first plane of the filter, right? How does this one guy contribute to this one element? So that is going to be W12 times Y12, right? Remember, the index of this filter and the index of the Z give you the index of the Y, right? So when I placed it here, it's Y12 times W12. But then when I slide forward, the same element now contributes to Z10, right? And what would be the index of the Y element that it multiplies? Anyone? Using the same rule? Someone? I'll wait.
Y22.
Y22, it's gone here, right? And that's because the index of the Z position and the index of the weight must sum to the index of the Y. So it's Z10 is W12 times Y22. So also Z20 is going to be W12 times Y32, because 12 plus 20 is 32, right? And now when I'm striding down, now it is Z1, this is Z01, this is W12, so the corresponding Y element must be 01 plus 12, which is Y13, right? Which is obviously what you've got over here. And so you can see that that one weight element contributes to every single one of these Z's by multiplying a different Y. So in general, ZXY is going to be W12 times Y. Observe this. You have to add these two elements to get the index of the Y, right? So ZXY is Y12 plus Y, W12 times Y, X plus 1, Y plus 2. So does this equation make sense to everyone? This is just a generalization of what we saw over here. You can check, you can verify that this always holds. And so if I were to generalize this for any ij in the weight, what would the corresponding equation be? Anyone? I'll wait. Yes, Ran?
Yeah, so for ij in W, the the corresponding position for y would be x plus I and y plus j.
Exactly. Thank you. Right. So this is what you're going to find. And so now if I want to compute the derivative, if I'm given the derivative for z, I want to compute the derivative for w. The derivative for z with respect to w is simply going to be, so the derivative for zxy with respect to y, wij, is simply going to be y x plus I, y plus j. I just pulled this straight out of this equation. Did that make sense to everyone? Raise your hands. Right. Very straightforward. There's nothing fancy over here. If you actually look at the equations, they may make your head spin. But well, a third of the class raised their hands. I'm happy with that. And of course, this is the derivative for z with respect to w. The derivative for the divergence with respect to w is going to be the derivative of the divergence with respect to z times the derivative of the z with respect to w, which is just this y term, right? And you'd have to, that's just for this one y term. But if you want the derivative of the divergence with respect to w, you have to sum over this plane. This plane of the weight influences exactly one affine map. So you would have to sum over all of the elements of the affine map, the derivative of the divergence with respect to that affine map element times the derivative of the affine map element with respect to w. This we have going backwards, and this second term is just this y term as we just saw. And so the overall formula for the derivative of the divergence with respect to every element in the filter is simply given by this kind of ugly looking formula over here. Now, formulae don't make, you can see how we derive the formula, you can actually code it in. But if you're like me, formulae don't make a lot of sense. You like to visualize things. What is this ugly formula exactly? It turns out it is just a convolution of the derivative map for z with y, right? This is exactly the same formula you used when you were convolving with y by w to compute z. Now going backward, you're convolving the derivative for z with y to compute w. There's no flipping. This is a straight up convolution, right? So if you don't understand how this is so, let's actually look at our pictures. Again, recall how we got our affine maps, these z maps. Each filter convolved with the entire set of activation maps, and then you sum them up to get the corresponding affine map. So during the forward convolution, the nth activation map of the previous layer convolved with the mth plane of the filter, of the nth filter, to compute the nth affine map. So to compute the derivatives for this filter, the only two things that are involved, because these are the only two elements in that are related by this filter plane. The only two things that are involved are the derivatives for the nth affine map and the mth activation map. This is for WMN. And here's what we're going to do. All I'm going to do is take this derivative map quite literally as is without any further ado, right? And I'm going to place this on my activation map of the previous layer and just perform a convolution. That's about it. And I'm not going off the edge, right? And that's going to give me the derivatives of the divergence with respect to every element of the filter. Now, this of course gives you the derivatives for only one plane of the filter. But if I took the nth affine map, the derivatives for the nth affine map of the nth layer, and if I convolved every one of the activation maps for the previous layer, I'll end up with the derivatives for every element of the nth filter. So did that make sense, guys? Raise your hands if that made sense visually. I'll wait for 50 hands to be raised. And hopefully that sort of helps you with your homework too, right? Because now you see exactly how the computation is happening. You have to sort of, I'm doing this only for the two-dimensional case. You'll have to figure out how to do this for the one-dimensional case. Now, what happens if the stride was greater than 1? You're going to have to do the same thing before. You're going to have to upsample this fellow before you perform the convolution, because you always want to work with the derivative map for the full affine map and not the downsampled affine map. Similarly, there was a hand raised. What was that? Yes, Pranav? Pranav and Tanya, go ahead. What are your questions?
Sorry, that was from the previous.
Okay, right, all right. So, and so also, if y was 0 padded in the forward pass, Philip, is that a question?
No.
Okay, all right. So if y was 0 padded in the forward pass, it must be 0 padded for the backprop. That's about it. But all the other, and you should be able to just look at these things and figure out how to adjust it to get the right size for the filter. The key point is if your stride was greater than 1 going forward, you have to unstride it to get the full derivative map here by introducing zeros before you perform this operation. And so I have pseudocode for it. I'm going to skip this pseudocode. And so we've seen how to compute the derivatives with respect to both the y's and the filters given the derivatives for the z's. Both of these are done, right? Now,
And we also have a poll for 306.
okay, go ahead. Have the poll. All right, stopping. Only 9. Okay. This is the second one is false. Why do you think it was true? Remember that to compute the derivative for one plane of the filter, you are only considering the activation map and the affine map that contributed it. You are not summing over all of these guys. So the second one is false. You have to read these things more carefully, because one filter plane only relates one activation map to one affine map. There is no further summation across maps. Anyway, so there's a cheap way to do all of this without worrying about the math of it, right? And that's this. Here is the computation going forward. If I just wrote all of these out, I'm going over the layers, I'm scanning the input, then I'm going over each of my filters, and for each filter I'm computing the computing the affine term by scanning, going over the previous filters, the previous layer maps, and adding the product of the weight and the activation from the previous layer map. I can also toss in the bias here for good measure, right? And then finally applying an activation. This is just the completely unrolled forward convolution. So we have the standard formula, right? Which is that we have, if I have y equals, y equals AB, then dl, and I'm given dl over dy, then I can say dl over dA equals dy over dl over dy times d, and dl over dB equals dl over dy times a. This is straightforward. This is just a standard chain rule, and we can just use that. So z equals wy. So if I have the derivative with respect to z, which is simply obtained by multiplying the derivative with respect to y by the derivative for the activation, then I can just say that the dy for the previous layer plus equals w times the derivative for z, and the derivative for w is simply going to be dz times y. So this w and this y term were multiplied to contribute the z. So going backwards, I just use this very simple rule over here, and the other change that we made is that now all of these loops are going from end to beginning. But other than that, you literally had to make very little change in the code. This is the complete backward code. So this is, and the code can be used just for stride and such like. So it turns out that although the mathematical explanation is very nice and it's very pretty, in my opinion at least, if you want to be mechanical about it, it is possible to be mechanical about it. And just take the forward code, reverse the order of the indexing, and anytime you have z equals w times y, you just say dw plus equals dy times z, or dz times y, and dy equals dz times w. So we've taken care of this. Let's go over to the pooling layers. Now, remember what we did for pooling. For pooling, we typically perform this with stride greater than 1, but then you just sort of scanned over a collection of windows, and you scan the input, and within each block, you just pick the largest value, right? So in max pooling, you always took the largest value. So if within this window you had 1, 3, 6, 5, you just chose the 6. Now the pooling itself is a two-step process. In the first step, what you did was you found the index of the largest value. So the first step is you're going to say, oh, within this window, the largest value is occurring at 0, 1. And then in the next step, you copied the value at 0, 1 out over here. So this means that these three guys really did not contribute to the output. So all I need to do, if 6 is the only one that contributed to the derivative, to the output, I have to, coming backwards, I've already got the derivatives for all of these locations, right? I just need this guy to copy the derivative for this one pooled guy out to the location of the max and plug in zeros elsewhere. So this is the max pooling derivative going backwards for max pooling. It's very straightforward. Now and this is performed independently for every map, right? Now there's one thing. If I just write out something of this kind, there's something broken about this equation. Can somebody tell me what that is? What's wrong about this equation? Anyone? What's wrong about this equation? How would you, so if your stride is lesser than the size of your window over here, would this equation be valid? Raise your hands if you think it'll be valid. If the stride is lesser than the size of the window. Anything on chat? Anybody making comments?
Nope.
So I'll wait. How would this be broken? What is wrong with this if your stride is lesser than the size of your window?
Could the same value be selected multiple times and the derivative
Exactly, right?
would be doubled?
So here's, now it's not going to be doubled, right? So let's say this element got picked up for the first position here. Then it got picked up again for the second position in the output map. So that means that when you're going backward, this has contributed to both, so both of their derivatives must be added over here. So you're going to say d loss over dy plus equals d loss over dz for the max location, and plus equals 0 for others. Did that make sense? Raise your hand if it did. All right. So this is assuming that at that pad there is only there is no overlap, right? And here's, so this was the max. Again, I have pseudocode. In the pseudocode itself, I've actually done the plus equals. If you look carefully. Now for mean pooling, what happens? You're taking the average of all of these guys, right? So if your mean pooling filter is k cross k, then you're summing all of these guys and dividing by k squared. And that element got copied over here. So if I have the derivative for this term, all 4 of these guys contributed to this derivative. But because they all contributed equally, this derivative has to be distributed equally over all 4. So this derivative over here is if this is d div over dy, I'm going to be doing d div over 4 times dy, because here my window is 2 cross 2, and copying that over to each of those locations, right? And so again, what is wrong with this equation here? Guys, what is wrong?
The plus equal.
Yeah, you need the plus equal again, right? If you have overlaps. But these are very simple derivative rules. For the pooling, the derivative rules are very simple. I'm just going to, I'm skipping the pseudocode, but take a look. The pseudocode is actually fairly clear. And so we've seen how to compute the derivative of the divergence with respect to every intermediate output and every free parameter. And this can be embedded into gradient descent to learn the network. Now, questions? Story so far. So the convolutional neural network is a supervised version of a computational model of mammalian vision. It includes convolutional layers comprising learned filters that scan the outputs of the previous layer, and downsampling layers. And what we saw was that the parameters of the network can be learned through regular backpropagation. Max pooling will only propagate derivatives over the maximum element, and overall derivatives must sum over appropriate sets of elements to account for the fact that the network is in fact a shared parameter network. So this is what we have seen so far. Questions? I'm going to do one last topic before I end the first session of this of today's class. Any questions? Raise your hands if you have questions. All right. So, yes, Ran?
Yeah, I got a question about the backwards for the max pooling. So for max pooling, if we got the max and fill in the position for the max position, and what are we going to do for the other positions? Are we going to fill in zeros, or are
yes? Why? Tell me why it is a 0.
Because they just don't contribute to the
exactly. So you fill in zeros. That's it.
But I just wondering, what if we fill in something just similar with the max position? Where
so the mathematics doesn't support it properly, right? So you could do it right, but you'd have to be very careful about it. What you're putting in is a subgradient, right?
Yeah.
And so you could. I'm assuming that there are smarter ways of better subgradients that could give you maybe slightly faster convergence, but the math tells you this is what it must be.
Okay. Thanks.
Right. There were other questions?
I was wondering, is there a way to compute the forward pass for the convolutional layer using matrix multiplication and some perhaps some
Haha.
shaping.
So it's there in the slides for lecture 8.
Oh, okay. Okay.
Remember,
Gotcha.
so remember, when you're going forward, the convolution, the entire convolutional network is just scanning with an MLP, right?
Right.
Scanning with the MLP is the same as having one large MLP,
Okay. Okay.
right? So you can
Right.
just compose the large MLP and and the problem is, the reason you don't do it is that the weights matrices are going to have large numbers of zeros. And so you'll be performing a lot of unnecessary computation.
By having a large number of zero, you mean that they shared a lot of parameters, or
No, but no, because if you look at the weight matrices, it's let's
Oh,
see.
okay. I guess what you mean. Yeah.
Yeah, right. I mean, because if I have some entries over here, and my shared computation, this guy over here, this input only looks at this, but it doesn't look at all of these. It doesn't connect to the other ones, right? So the
Right.
weight matrix
Okay,
is
yeah.
going to have some values and the rest are zeros. And you're going to have a lot of zero multipliers. Take a look at this.
Okay. Yeah. Okay. Cool. Thank you.
And we were in fact thinking that if anybody discovers this for the homework, we'll give them bonus points, but nobody did. All right. So now we always assume that subsequent steps shrink the size of the maps. So, if you had a stride 1, then the output map was the same size as the input map, modulo the boundary effects. If you had a stride greater than 1, then the output map is smaller than the input map, right? Can we do the reverse? Can I go from a small map to a larger map? This is like having a stride that is less than 1, right? How does one accommodate a stride that is less than 1? So again, this is the vertical picture, right? This is if I were scanning with an MLP, then this is the little MLP that's scanning my input. Here I have very large strides. Again, this is to answer the previous question. You can see that if I just directly use this MLP, this guy only connects to these 3, so all of these other weights would be 0. Anyway, so if I was scanning with an MLP, what happens is maybe the first layer, if I were performing a convolution, the first set of filters, they look at some inputs, then they take a stride, then they look at a bunch of inputs, they take a stride. Then the next layer, so because they took a stride, the number of vertical bars over here is lesser than the number of input bars. The next layer is going to do the same, so the number of vertical bars in the next layer is going to be fewer than the number of bars over here. And so scanning basically maintains or reduces the time resolution of the input at each layer. Here you have a very large number of inputs, but at the output of the first layer, you just have 1/3 as many in this case. And the output of the second layer, you're going to have 1/3 as many as the second layer, which is 1/9 as many as the input. So every time you go up, you're either maintaining the size or you're reducing the size. Can I have the situation where my first layer reduce the size maybe by 1/3, but then in the next layer, I want to have maybe as many outputs as the number of inputs, right? What would be the problem with trying to do something of this kind? Anyone? What would be the problem with trying to increase, in this one-dimensional case, the time resolution with the layers? What would the problem be? Somebody.
Would we get a bottleneck issue?
Pardon me? A
Would it
bottleneck?
be?
No. Just tell me, how are you going to compute this guy?
You don't have the inputs.
You don't have the inputs, right? So all of these guys don't have, if you want to compute this one, the 3 input it requires, none of them are available. For the majority of these guys, the inputs that they need, you see all of those arrow beginnings with nothing below them, those elements are missing. You cannot scan, right? What would your solution be? Yes?
Do the broadcasts.
Pardon me?
Do the broadcasts like for the.
I'm not no broadcast. This is again, these things are missing, right? They're giving me a Python solution, but those elements are missing. So yes, Sive, what would you do?
You'd have a smaller stride initially.
Okay, I can just introduce zeros, can I not? I can just introduce a bunch of zeros and say, now go ahead and scan. And you're going to get a larger scan, larger resolution output.
But how does that help you?
You're basically sort of, these things don't really have information. Remember, in a neural network, consider this. We answered this in Piazza as well. Remember the double pentagon example? In the double pentagon example, the input was two-dimensional, but you had 10 neurons in the first layer. Why was that? One set of 5 neurons captured one pentagon, the other set of 5 neurons captured the other pentagon, right? So when you have a larger resolution output than the input, you can detect a larger number of features. So that's one of the things. And here, if you're trying to reconstruct this input, if you're trying to reconstruct the input, for instance, you're going to have to increase the resolution, but there's stuff missing. So the only solution is you're going to assume there's information lost, but to get the time detail, at least the same number of inputs, you're going to have to make assumptions about these guys, which you never computed going forward. And your best guess is 0. Now, does it have to be 0? It doesn't have to be 0, right? You could very well have been interpolating between neighboring guys and putting these fellows in, because that's you could guess that this thing is going to be something between this and this, right? Does that make sense to you, fellows? I'm going to go 3 minutes over. Raise your hands if this made sense. So introducing zeros is not the obvious, most sensible thing to do, clearly, right? If you have more information about what those intermediate values could have been, like it's a smooth continuation, then you could have just interpolated or anything else. But in the absence of any other information, just introducing zeros is the simplest thing to do. And this is exactly analogous to the upsampling performed during backpropagation, when we did the forward convolution with stride greater than 1. It's the exact same analog. The stuff that you don't know, you just introduce as 0, right? And so, of course, these 0-valued inputs, if you're just making them 0, they don't really provide any input. They and their connections, you can make them virtual. I can just sort of remove them and pretend they exist, but then the computation kind of changes a little bit, right? Because now you're not explicitly introducing their contributions. So now when you do this, or even if you regardless of whether you explicitly introduce zeros or just pretend they are zeros and only perform the minimal computation, which is the computation you'd have over here, something happens. Now remember, when you were going forward in the lower layers where you had downsampling or you maintained the size, the parameters for every column were identical, right? But when you're upsampling in this manner, the parameters for the columns are no longer identical. This guy, for instance, everything that has a red arrow over here is looking at only one input. Everything that has a green arrow over here has a short distance to the left and a long distance to the right. So all the green arrowed inputs, the columns, have a different set of parameters than the blue arrowed columns and the red arrowed columns. So you can think of all of them as having virtually the same set of parameters, but then some of them connect to zeros, right? So practically speaking, these guys, the red guys, are similar in structure, the green guys are similar in structure, and the blue guys are similar in structure. If you look carefully, the red guys connect directly on top of the lower bar. The green guys are to the right of it, and the blue guys are to the left of it. So they have different structure. And so this means that you can't just use your regular convolution without explicitly introducing zeros. If you don't want to explicitly introduce zeros, then this is going to come back to bite you. Yes, Ibe?
Sorry, I was so confused. So for this upsampling, is it supposed to be part of a classifier or still part of the feature generation from the convolutional network?
So your convolution net could very well have intermediate layers where you have where you're upsampling.
Okay, but when you talk about inserting some artificial values between like zeros, you say that you call these as intermediate values, like they you can get into how they intermediate in what sense?
So if I'm introducing zeros, you're not using any intermediate values. You're just using zeros over here, right?
Right.
But what you could also do is you can take a guess at what these columns could have been had you actually scanned the lower layer with finer resolution.
Okay. Okay. So you're talking about the case where you have actually like more smaller stride size for the lower layer, or
What I'm saying
like,
is that so again, these zeros are assuming you know nothing about what would have been computed here had this layer had a finer stride size, right?
yes.
But you can take a better guess. You can say that this one would be 1/3 of this, 2/3 of this guy, and 1/3 of this guy, and have a
Okay.
linear interpolation, right?
Okay.
Right. We don't do that because it complicates things. If you actually filled in these intermediate values, the next layer is just going to be a standard convolution. If you don't, then you end up with different elements in the next layer looking at different numbers of inputs from the previous layer. So, and so when you look at the upsampling, this is the kind of the computation that you have to perform changes a bit. The entire computation can still be viewed as scanning the input with a shared parameter MLP. So in this case, this would be the shared parameter MLP. Here you can see that this layer is upsampled with respect to the pink layer, but then the computation has changed slightly. In the now in the lower layers, typically what happened was that these guys would read from the lower layers, right? When you had when you were maintaining size or when you were downsampling, as you scanned left to right, these elements would read values from the lower layers and then compute their output. If you're upsampling, you're going to do something different. These upsample layers are no longer going to be reading values from the lower layers. Instead, the lower layers are going to be pushing values to the upper layers. So you'll be multiplying by this weight and adding to this entry, multiplying by these weights and adding to these entry, multiplying by these weights and adding to these entry. And so you'll be scanning, you'll be going left to right over the lower layer, and the lower layer values would be pushing their values up to the next layer so that you can compute the next layer. This is again just the manner in which the computation is performed, and it's kind of useful to see why that must be the case. And so if I wrote this in vector form, in regular downsampling layers, you computed the affine value by multiplying the previous layer outputs by the filter. Now, what you're doing is that the previous layer filter is sort of, so this guy was multiplying the previous layer by the weights matrix to compute its output. Now, this one will be multiplying the transpose of the weight matrix for the next layer because it's pushing up rather than having these guys pull their values from below. These guys are pushing their values up, so they must be multiplied by the transpose of the filters, which is why the whole thing is called transpose convolution. That's just for terminology. So what I'm going to do now is I'm going to stop right here. I'm going to stop the recording. If you guys have any questions, actually no, wait. Let me do this for a couple more minutes. I'll just show how you do this for 2D. Same thing for 2D, right? In 2D, it's the same thing. If you wanted to upsample, you're going to introduce a bunch of zeros and then convolve with the filter and you get the output. But procedurally, you wouldn't actually explicitly upsample it with zeros and convolve. What you would do instead is something different. You would create an output map of the size that you would get if you had upsampled these terms. And then you're going to strive for, you say you want to compute this map which is b times the input maps. You're going to create an empty map which is b times the size of the input map. Now the filter size has nothing to do with the expansion factor. The filter could be anything, right? And then we multiply the first element of the input map with the filter, add these up, and you're going to fill in the first element of this block, of this upsampled map. Then you multiply the next element of these inputs by the filters, sum them up, and then you're going to stride forward by B over here, and then drop the result into that location. Where there's an overlap, you will just add things. And then the next element is going to multiply these filters, and then you're going to stride forward by B again, and just drop the output here. The overlap regions get added, and this is how you would actually compute your output. You'll observe over here that some locations get a contribution from only one position, some get it from 2, some get it from 4. That's simply because of the whole upsampling process. Again, this goes back to the same figure we had previously, which showed that different regions of this output map get contributions from different elements of different sets of elements in the lower layer. So pseudocode again. And backprop for this, it's very straightforward. When you compute your backprop, you're going to get the derivatives for the upsampled map. And then you're going to have to downsample from this upsampled map to get back the derivatives for the previous layer activation maps. So this is the convolution. So I'll stop right here. I believe there was another poll.
Yes.
So just let's just do the poll, and I'll stop the recording. Okay, let's stop. And the answer, of course, is this is what we've been saying. This is exactly true. This is exactly what happens when you have these upsampling scans, when you're increasing the resolution. Right? So this is true. So guys, I am stopping the recording.